one of the mysteries about electrons is, why are they all the same? It's not been clear. And one of the possibilities is they're only the same from the outside. The electron on the inside, so to speak, is a structure that contains knowledge of its history in a way that is just not visible from the outside, so to speak, much like for a black hole.
I wanted to get back to particles. I like this idea that particles may be persistent tangles in the hypergraph and maybe even tiny black holes propagating through the hypergraph. I know this isn't fully worked out yet, but my worry about that idea is, how do these particles maintain their integrity with all sorts of rewriting of the hypergraph going around on the periphery of the tiny black hole or whatever it is? How does an electron remain an electron consistently forever?
Right. Well, I mean, what is a particle? A particle is kind of a lump of existence that kind of can be propagated through space and time. It's something that maintains its identity through space and time. Now, it doesn't maintain it forever. It's going to, even in particle physics or whatever, it's going to scatter against another particle. It's going to change its identity. It is a thing that, for a reasonable period of time, we can identify as having a definite identity. So, for example, a good analogy of this in a quite different physical system would be an eddy in water.
Yeah.
So, that's something which for a certain period of time, it maintains its identity, its integrity, yet it's made of different molecules at every separate moment. So, the analogy there in the hypergraph is we imagine some kind of topological tangle where the thing can, like that vortex, where the vortex doesn't dissipate immediately because the thing's on the opposite side of the vortex. It's kind of like you've put a piece of string around a pencil. You can't, even if you pull on the ends of the string, it's not going to untangle itself because it's kind of wrapped around the pencil. And that's what's happening in the vortex. And sort of a generalization of that is what we imagine is happening in the hypergraph in kind of defining the structure of a particle. Now, I suspect that picture is kind of just a toy model. I don't think that's really what's going on. And I have to say, it's kind of just to give some sense of scale of these kinds of things. There are theorems about kind of for example, in graphs that are planar, where you can just lay out all the edges on a plane without any crossing. There are theorems that say when there is non-planarity, it must always come in these certain particular lumps. It's a theorem from, I don't know, about 100 years ago now. And as I've been working on sort of developing the physics project, I was looking for generalizations of that theorem. It just gives some kind of sense of scale of what we're up against, that, talking to some sort of top graph theorists a few years ago, the basic answer when I said we need these theorems that are big generalizations of this, their answer was, come back in 100 years and we may know a bit more about this.
Right.
So it kind of gives one a sense of scale of what the technical difficulties that are involved are. But I think this notion of sort of the topological tangle is probably just a toy model.
Okay.
And I think one feature of black holes is that there are many features, but that they again have this feature that they're this kind of lump of structure in space-time that has a certain coherence to it. One bizarre feature of black holes and particles is this. In a black hole, there could be some whole civilization living around some star somewhere. Eventually it turns into a black hole. That whole civilization is crushed into the insides of a black hole. But to the observer outside the black hole, all they get to see is this nice, smooth event horizon of the black hole. And it's like that whole civilization inside, we don't know about it. Every black hole of a certain mass and angular momentum, effectively, is the same.
Yeah.
Well, one of the mysteries about electrons is, why are they all the same? It's not been clear. And one of the possibilities is they're only the same from the outside. The electron on the inside, so to speak, is a structure that contains knowledge of its history in a way that is just not visible from the outside, so to speak, much like for a black hole. Now, this question of, what is the actual sort of underlying, so what a particle is something which somehow is a carrier of pure motion. It's not obvious in our models that motion is possible at all. It might be the case that you have this thing that exists as a structure in the hypergraph, and that structure could never be just sort of transported to another part of the hypergraph and stay the same kind of thing.
Yes.
It's just like the fact that there are eddies in water that can maintain their integrity is not something that's obvious. It's something you have to derive from the equations of fluid dynamics or whatever.
Or like gliders in Conway's Game of Life, it's not obvious that there would be things in Conway's Game of Life that can persist through space like that and maintain their integrity. Yeah.
Right. So it's a thing you have to derive.
Yeah.
And the fact that motion is possible is something, again, it's something we take for granted. By the way, the fact that we take motion for granted is probably a consequence of the fact that space-time is pretty tame around where we are. If we were near a bunch of space-time singularities, we absolutely would not take motion for granted. If I move this, glass, right now it seems like it stays more or less the same thing. If there are a bunch of space-time singularities, it will be shredded into its elements, so to speak, whenever we move it around, and we wouldn't believe in pure motion. I mean, it's another one of these things. Observers like us believe in pure motion. And particles are the carriers of pure motion. Black holes are also carriers of pure motion. Now, one thing that is a very recent thing I've been thinking about, let me back up a little bit. One of the things that surprised me in the physics project is that we were able to get a representation of energy that did not require us to understand what particles are.
Yes.
So I had thought we wouldn't know what energy was until we knew what particles were. But in fact, energy is roughly just the amount of activity in the hypergraph. It's, you have to define it a little bit more precisely when you're dealing with space and time and reference frames and things. But when you think about the causal graph that relates the different events that happen in the rewriting of the hypergraph, we can think of energy as the kind of flux of causal edges that go from one event to another, slicing through space-like hypersurfaces. But in any case, it's basically the amount of activity in the network, and that's sort of a bulk measure of energy, the density of energy in the universe. So my assumption had always been that to talk about particles, we'd actually have to know how these tangles work, and we'd have to understand the topology of them and so on. But then I start realizing that actually in particle physics, it's actually taken a shortcut. Particle physics doesn't really understand what particles are made of. In the fundamental theories of particle physics, quantum electrodynamics, quantum chromodynamics, the Standard Model, and so on, particles are just thought of as these indivisible kind of points that have world lines that go through space-time, so to speak. If you say, I really want to have a realistic model of a particle, I want a realistic model of a proton, for example, that's a very complicated thing. Nobody knows how to set up the kind of the configuration of the quarks and gluons and so on to represent a realistic, whole, messy proton, so to speak. It's just we know how to think about a quark, a gluon, or an electron that we can think of as a point particle. And in fact, what I realized recently is all we really know is the carrying of causality by those particle-like things. So what we know is there's an electron, it interacted with a photon here. Then there is the knowledge of that event is carried to another event by this kind of world line of this electron. So in my friend Dick Feynman's great invention of Feynman diagrams is kind of a representation of kind of how the events, the interaction of particles here, how that relates to another interaction of particles somewhere else. And in Feynman diagrams, you're just drawing a bunch of lines. Sometimes by convention, you draw a photon as a wiggly line, an electron as a straight line. And what's happening in a Feynman diagram is you're representing kind of the causal connections between these interaction processes at different places in space-time. And so a Feynman diagram is essentially a causal graph. This is something I realized only recently. And the Feynman diagram doesn't talk about the details of what's inside the particles. It's just talking about the carrying of causality through these particles. And so that's something that I think is much closer to a thing that is accessible pretty directly in our models. And and in fact, I've just been sort of looking at this idea of what one can think of as sort of infra-Feynman diagrams, so to speak, this kind of lower level carrying of causality that then one can sort of aggregate up to think about sort of actual particles. So my guess is that my current guess is we're going to get quantum field theory without knowing what a particle is, which is how quantum field theory works as well, by the way.
Right.
In quantum field theory, the one of the terrible things is that when you work out kind of a scattering process, you're working out the S matrix, the scattering matrix, that says we've got this set of particles coming in, we've got this set of particles going out. It's kind of like, well, what happens in the middle? That's the sort of where there's interactions, and you can represent that using Feynman diagrams and so on. But if you say, what really came in? It's not a big fluffy proton. It's some representation of plane waves of these idealized point particles. It's not, and in fact, we've been able to get unbelievably far with particle physics without ever really knowing what's inside one of these particles. If we say, we know roughly protons have quarks and gluons in them, and there's some complicated configuration of fields and all this kind of thing, and if you say, I need to know if I'm going to have a, in quantum field theory, there's a kind of, as one tries to axiomatize quantum field theory, it's sort of okay when you're talking about these particles that are not really interacting very much and off at infinity separate from each other. But a proton is not like that. A proton has a bunch of quarks and gluons that are always interacting all the time. And so you don't get to kind of tease it apart into this thing that quantum field theory can talk about. So I think we're going to, I kind of should have realized this earlier because I've known quantum field theory since I was a kid, so to speak. And I've sort of been the kind of concept that that you can kind of think about quantum field theory without really even knowing what a particle is something that I hadn't internalized until very recently, and I'm pretty sure we're going to be able to see how quantum field theory comes out of our models in a much more direct way without having to say what a particle is. I mean, both for us and quantum field theory, it'd be really nice to know in more sort of ontological detail what a particle is, but that hasn't been the last 100 years of quantum field theory, and it's a good way into what we're trying to do and sort of connecting with quantum field theory to deal with that. It will be a separate step to really say this is what a particle is in a more sort of ontological fashion, and to say, is a particle really a black hole-like thing? I mean, I should say this notion of preparing the initial conditions for an experiment is a horrible can of worms.
Yes.
When you do that, for example, you're looking at the merger of two black holes. Okay, you've got this space-time metric in standard general relativity that represents these two separate black holes. It's a very complicated art to set up the kind of right initial data to be able to see these black holes merging and to not get confused about sort of the way that you're slicing space and time and so on. It's a strange thing. It's a strange thing where you're almost assuming the answer as you set up the initial conditions. It's just, again, a piece of extreme technical difficulty that we have a version of in our models that in a sense is clearer, I think, than it is in sort of the traditional approach to physics, but still we don't get out of that free, so to speak.
Yeah. That's fantastic. I do hope we make progress on particles. It just seems like it's one of the biggest things that's going to be a challenge to describe. But like you say, it's been a challenge for quantum field theory to describe what's really going on as well.
I am rather optimistic that we're going to be able to get quantum field theory, that we're going to be able to get a correspondence between our models and the standard formalism of quantum field theory. And so we then get to leverage, as we have done in other places, we then get to leverage the successes of quantum field theory.
Yeah.
And I think that these questions like, why are all electrons identical? That's a question that I don't know whether that's going to be addressable. In quantum field theory, that question is not addressed. It's just taken for granted. I think we may be able to get to in a place where we can we can really start to address a question like that. I would say that on this notion of what particles are, these carriers of pure motion, the things that I've been thinking about, not really figured out. I'll talk about a couple of them. So a particle is a carrier of pure motion in space-time. Next question, what's the analog of a particle in Branchial space? What is a carrier of pure motion in Branchial space? My guess is that it is related to virtual particles. In quantum field theory and quantum mechanics, there's this idea, you have an electron, it's a happy electron, it has a mass of 0.511 MeV or whatever, it just is an electron. But in quantum mechanics and quantum field theory, you can have an electron that's emitted at some moment and then absorbed a very short time later, and that electron won't have the exact same properties as an ordinary sort of separate, free, independent electron has. For example, it won't necessarily have a mass of 0.511 MeV. It may have a different mass temporarily. It's a limited time electron, so to speak. And that's in quantum field theory. The whole structure of the theory is based on this idea of virtual particles that live only for a limited time. I mean, the basic structure of quantum field theory is to say we're looking at scattering processes where particles come in from infinity. Those particles are acting like free particles, independent of everything else. At infinity, they come into some region where they're interacting. Then all the things that happen in that interaction are lots of these sort of limited time particles being exchanged, these virtual particles. And I have this suspicion that motion in Branchial space is somehow related to virtual particles, but I haven't completely untangled how that works. Beyond that, I will say that there's a question of motion in Rulial space. And that, I think, is a little bit clearer what's going on. In Rulial space, sort of different places in Rulial space effectively correspond to different assumptions about the rules by which the universe operates. As you're in a different place in Rulial space, it's kind of like you're projecting the operation of the universe into a different sort of basis in terms of what rules you're attributing to what's going on. And in a sense, we can think of different minds as being at different points in Rulial space. Different minds have different points of view, different ways of internalizing how the world works. And then the question is, well, what's pure motion in that setup? And I think the answer is that, in a sense, concepts are the analog of particles. So what we're doing is we're taking some sort of assumptions about how the universe works at some place in Rulial space, and we're having to package up what we think about and transmit it to another place in Rulial space where it can be unpacked. And I think this concepts are sort of the way of packaging up kind of things that are being thought about by one mind in such a way that they can be transferred to another mind. And it is an amusing fact that I don't fully understand yet, that we have discrete words and we have discrete particles like electrons, that both these carriers of pure motion, so to speak, both in space-time and in Rulial space, seem as a practical matter to be sort of discretely, we can label them discretely. And we were talking earlier about kind of the representation of knowledge and so on. And I kind of have this slight suspicion that there is something sort of a set of big results one can have about kind of the spreading of knowledge across Rulial space and this notion of packaging knowledge up into concepts and so on, and its analogy with particles. I think the thing that sort of is a big picture of the physics project is, given the sort of paradigm that's emerged, being able to see sort of how does that paradigm spread across these different kinds of space, across these different kinds of areas that we've thought about as in the development of science and so on. And that's, you had asked me earlier about what I find most exciting about what's going on. And I think it's this fact that we really have this kind of paradigm that can be, where there are amazing analogies that can be made across these very different areas. I mean, I would say that in my life, I've been lucky enough to be, I guess, involved in a couple of different sort of paradigms in the making, so to speak. One of which was just the idea that you can use computation and programs to make models of things rather than things like mathematical equations. And that paradigm is now reasonably well understood. And that paradigm also had the feature that it let one take things that one observed in one area of one domain and immediately sort of translate them into another domain, things like computational irreducibility and so on. With the physics project, we have this other paradigm that is sort of wrapped around the Rulial and observers and multi-way systems and all that kind of thing. And we're just in the very early years of kind of understanding how that spreads across all these different areas. And it's awfully exciting as far as I'm concerned, because it's kind of it's just this very fertile moment where you can kind of see, you've kind of reached a different level of the tower, and you get to see the landscape, a lot further out in the landscape. I would say that the thing to realize, though, is to really sort of relate what we're doing to everything that's known. There's a lot of technical work to be done. And I would say that if I'm to sort of give an assessment of where we're at, I would say that the paradigmatic side of things is maybe a century ahead of schedule, so to speak. The technical side of things is, it's just hard work, and it's going comparatively slowly. And I don't know, the years, I think it will accelerate a bit as more technical things get done, as we figure out how infrared geometry works and so on. We'll be able to build on that, and it will be easier to do the next stage and so on. But that's a little bit, I would say, to me, that's the thing that is sort of dragging the most, so to speak, is filling in all these technical details.